Welcome. Happy Monday. Almost the last week of classes. We see each other on Monday next week. And then it's final exams. Oh my gosh. We'll have a final project, so we'll talk about that on Monday. And it will be due December 15th. Okay, so we will discuss the final project in class next Monday, which is our last class. I have to. But I want it to be bigger. No, I need it to be bigger. There. How about that? So next Monday is our last class, and then there are no more classes, right? And then so we don't have a final exam, right? But we do have a final project. And I know, I'm sure you guys are ready for a little bit of a break though. And I think I saw that I get to see a lot of you in January again, so that's nice. Not because you failed, you signed up for a different course, so that's fun. Yeah, so okay, so we'll leave that final project, but the final project I'm gonna say is due December 15th at 23:59. I have a meeting with Joe this afternoon, so if that changes, then that I'll let you guys know. But that's when I want to have it due. Okay. So, and that should be it. Okay, so another thing. Remember quiz 4, so no class time on Friday, but if you want to, the design is you can use that time to do quiz 4, but just like the other quizzes, it'll be open from Friday until Sunday night. Okay, so you can use that class time to do quiz 4, that's the idea, but then you can do it whenever you want. So quiz number 4 will open on Friday and close on Sunday at 11:59, of course, PST. And I guess I should throw that on there. Only because I know we're dealing with all these time zones, but of course it should be presumed that we're working in Vancouver time and Kelowna time. So it'll be open on Friday and close on Sunday, and 50-minute timed quiz with 20 questions, just like before. With 20 theory questions. So nothing applied, just like before, so no R code, right? So theory is just meaning no R code. Okay. So everything from the textbook, everything that we talk about in class, just like before. Okay, so I will say no in-person lecture on Friday, right? You can use the time to do the quiz if you want to. Oh goodness, no, it's just from chapter, I think we did Quiz 3 was on 6 and 7, I think. And then quiz 4 will be 8 and 9. Yeah. Oops. And I'll say here, quiz number 4 is on chapters 8 and 9. Yeah, don't worry. That'd be terrible. No. Breaking it up into little bite-size sections. Okay. So, and then that, of course, will be our last quiz. And good. Okay, so last Friday, or at some point, hopefully over the weekend, you watched my video, and I thought it was so funny because I had a moment in the video where I was like, this isn't going to work out, but then because I was doing it on the fly, and then anyways, I thought about cutting that out, but then I made it look more real, so, which it was, but we worked through it, so whatever. Pretty minor, but just kind of funny. So for review, which was on the logistic regression video. Okay. What did we say? Well, if we're trying to classify, and when I say classify, or when we say classify, what we mean is we have some categorical binary, so 0, 1 outcome, and we want to classify or make a prediction for a future outcome, right? And so that's what classification is, and logistic regression is a way for us to do that. Okay, so logistic regression is a classification method right? And the classification method means that we have some binary, which means categorical outcome. Yeah. So binary, remember, is 0, 1. Okay, so either it happened or it didn't happen. Okay. So it's a classification method where we can predict the probability of being in class 1. Okay. It is a classification method that predicts the probability an outcome will be in class 1. Yeah. So we talked about the log odds, and that's what we model. So what's nice is we can take those concepts that we took that we learned in multiple regression or even simple linear regression, and we build a linear model. And then the thing that changes is that now, because I'm modeling the probability, there's some restrictions on that, right? Probabilities can only be between 0 and 1. And so I want to put restrictions on there. But if I'm modeling a probability, then I can do that because that is a numerical outcome, right? A probability is a numerical outcome. So what we do is we model the log odds. Okay, and we said the odds of something happening is the probability of it happening over the probability of it not happening, right? And so, and then we take the log, which is the natural log of that, and that becomes our response variable, right? So we said, okay, we've got the log of, and I think we use p hat for notation, yeah. And you know what, I'm just gonna go for the ln, the natural log. But when it says log in anything but physics, they mean the natural log. in statistics, in, I don't know, pretty much biology for sure. Yeah, we mean the natural log. P hat over 1 minus P hat. Oops, oh my gosh. Okay. So here, these are the odds. Okay, so that's the probability of something happening over 1 minus the probability of it happening, which is the probability of it not happening, right? And so this becomes the log odds. And that all becomes the numerical outcome that we build our linear model for. Okay. So then we have B0 plus B1 x1 plus B2 x2 plus all the way to BP xP, let's say, for P predictors. So then this becomes the numerical outcome that we can model with, with a linear model, right? And then this is, of course, our linear model. Shouldn't say of course, but it is our linear model. Okay, so that's the trick. Now, interpreting this outcome, right? We can predict values, we get the slopes, and we get the coefficients, and then we can plug in values of x, and then we can get predicted log odds. Okay, but we have to take those log odds and we need to turn them into just the p hat, which is what I'm interested in, right? And then so what we end up with is, where is it here? Just grab it here. Oh, maybe not. Is this logistic function, which looks like this. I didn't want to write it out because it's kind of long, right? But then once we have a model, right? So once we have coefficients for B0, B1, B2, blah, blah, blah. Oh, I guess they used Q. I should change that because I used P, but that's okay. It doesn't really change anything, but just to match there. Okay. So once we have a prediction for the model, right, then I can take e to the negative of that prediction and then 1 plus that and then 1 over that for the predicted value of p hat. Okay. So what we do, and maybe I'll use a different color here, plug in the linear model prediction. Okay. Then you will have p hat. Okay. Once you have p hat, then you can classify that outcome as being either in the 0 class or in the 1 class, because remember, this p hat is the probability of being in class 1. And maybe what I'll add in front here is if the probability of being in class 1 is greater than 0.5, and that's our typical cutoff, which makes sense, right? If it's more than 0.5, then we call it a class 1, right? If I tell you that the probability of this outcome is in class 1 is 60%, you wouldn't predict that it's in class 0, right? You would predict that it's in class 1. And why? Because it's more than 50%. So we have that cutoff built into kind of our minds, right? So don't be thrown off by it being said explicitly. You have it, right? That's what you would do naturally. So maybe I'll add here, if the probability of being in class 1 is greater than 0.5, right? We predict it will be in class 1. And I'm trying to keep all the review from last day on the same page, but it's getting a little bit crowded. Nice and lofty up here though. Oh well, if the probability being in class 1 is greater than 0.5, we predict it is in class 1. Right? And then we've already talked about, okay, then we have methods for figuring out what our error rate is, because what we do is we take those predictions and we compare them to what actually happened, because otherwise we won't be able to determine how well our model fits, right? And so it's this whole process of, okay, we split our data, we have our training data, we build our model, and then we check our model. How did our predictions work out, right? Did our classification scheme here, does it do a relatively good job of predicting the actual outcome? Then we apply that model. Once we've decided on a core couple of models that we like, we apply those to a new data set, right? What's different here, that validation data set, we haven't built the model from this validation set, right? So this is our first chance to show off how flexible our model is, right? How good of a job is it going to do on new data, which is important, right? We've talked about this idea of overfitting quite a bit, right? Where we model our training data so well, captures every little nook and cranny in our training data. But then when I go and I take that mold and I try to put it on a new data set, that's not how the new data set is going to behave. So then how it performs is not going to be good, right? In comparison to how it performed on the training data. Then we use the validation set. So we've got the training data, we built our model, we pick the best ones, apply them to the validation set. And that's when we, let them go head to head, and which model does the best at predicting the outcomes, the actual outcomes in our validation set. From there, we pick the best model, right? Probably the one with the fewest errors of different sorts. And maybe there's a trade-off there, right? Maybe your class 0 error is really low, but your class 1 error is kind of high. That depends on the data, right? What you're willing to put up with. But usually you're trying to strike kind of a balance. And then once you've picked your best model from the validation set, then you apply it to the test set. And those measurements, how well your model performs on your test data, that's the one that you report, right? That's the one that you feel comfortable telling people about. Oh, we were able to get this and that. Oh, wow, oh, that's crazy. So good. That was a quick recap of what we've done in chapter 9 basically so far. And so the next concept is kind of a cute concept. It's the KNearest Neighbors. Again, it has to do with classification and estimation. Remember, estimation is if we have a numerical outcome, right? Whereas classification is if we have a categorical outcome. We're going to stick to binary outcomes, so make it even more precise there. So the KNearest Neighbors approach, in its most basic form, says that, okay, if I want to predict the outcome of some observation, right, then I look at things that are close to it. So measuring close to it on a numerical scale. And then I look at what the outcome is for those observations. And then I just pick the one that's most frequently, oh, you're in class 1, you're in class 0, you're in class 1. 2 out of 3 are in class 1, so I'll be class 1 too, right? I should say class 1 as well, right? Don't want to incorporate another 2 in there, no. Okay, and so kind of cute because it just looks around in the data set and says, well, these are the things that are closest to me, and that this is what's happening with them. So I'm going to be the most occurring class that I see around me. Okay. And so one thing that's going to be really important is, well, when we let our observation look out at its k-nearest neighbors, we need to determine, well, what are we going to measure, right? The k-nearest neighbors, the nearest neighbor part is based on what, right? What's a good variable to look at in terms of what we're close to? Okay, so usually what you have to do is you have to kind of sort through your data, and maybe there are some variables that are kind of more telling than others, okay? And so let's see here. You want to have a low enough number of features that you're looking at, so variables that you're looking at, because otherwise the distances, if you're looking at too many things, oh, I'm 4 away from this variable and 3 away from this variable and 4 away from this variable, 5 away from this variable, you're being pulled in too many directions. So each observation is being pulled in too many directions. And then you're not going to be able to pick up on anything. Okay? So I think this is easier if we just have a look at an example. And we can use, so one thing to remember is that we can use k-nearest neighbors, and the k is just looking, so the k just stands for how many of your nearest neighbors are you looking at. And what we'll do is we'll vary that number, right, from 0 to whatever, maybe 1 to whatever. Can't look at 0 neighbors and make a prediction. You have to look at least one nearest neighbor. Right? If k is 1, then you just find your one nearest neighbor, and that's what you're going to predict that you are. Right? We can also estimate continuous outcomes with k-nearest neighbors. Then it takes the average, but we'll get there. So just kind of parking lot that. But I like to start with categorical outcomes because it's a little bit easier to think about. But then the same idea applies for numerical outcomes. Kind of nice. Wonder if this is all one piece, for better or for worse. So this is for categorical outcomes, and the k is just number of neighbors to consider. Okay. So we call k-nearest neighbors a lazy learner because what it does is it just looks at the entire training set and kind of lays everyone out, and then we're able to make predictions based off of all those training data sets. Whereas in logistic regression, right, we built a model and we use the training data set, but then we're able to have those coefficients that we can apply, right? And so the k-nearest neighbors just relies on what's happening in your training data set. The other logistic regression and all regression does as well, but having those coefficients means that we can take it and apply it to something else. Okay, so let's see here. Let's see here. When KNearest Neighbors is used as a classification method, a new observation is classified as class 1 if the proportion of class 1 observations in its KNearest Neighbors from the training set is greater than or equal to the specified cutoff value, which is typically 0.5, right? Which is probably what you would go for anyways. So in terms of what does that look like, I've got a oh, it's way down here. Okay, maybe I'll hold off just a little bit, but just you can scroll ahead and you can have a look at the KNearest Neighbors situation. But I guess I want to talk about this stuff first. It's how I laid it out. But honestly, it was like last week that I laid this out, so it's not, the groove's not there yet. Anyways, so what we're doing, right, is we're just saying, okay, if these are the variables, right, so if these are the observations in these variables, right? So, sorry, one row of data will have certain outcomes for a set of variables, right? So for that set of variables, then we can look at, okay, then I can measure how close my new observation is to some of those outcomes for each variable, right? So I can measure distances from a certain number of variables. Now to visualize, we usually just have 1 would be easy, but 2 is fine as well, because then I can have variable 1 on the x-axis and variable 2 on the y-axis. That would be fine, right? But for visualizing, then we kind of stick to 2 variables. We can have more, but then it's hard to visualize. So I like to think of it as I am plopped on some plot, right? And I am the observation that I'm trying to predict the class of, right? Because we're talking about the categorical outcome, I'm trying to predict what class am I in, class 0 or class 1. So then if I'm told that K is 3, then what I do is I span and I increase the radius of my span until I've hit my 3 nearest neighbors, okay? So then I look at the outcome of each of those 3, and then I become the most frequently occurring outcome. If it's a 50-50 split, not at 3, but let's say I go to 4 nearest neighbors, then I could have 2 in class 0 and 2 in class 1. So then I would classify as class 1 because the cutoff value is 0.5. And let's say, just to clarify here, class 1 if 0.5 or more of the neighbors and I'll just underline that here, are in class 1. Right, so it's inclusive of that 0.5. Okay. So what can we look at? If I look at my 1 nearest neighbor, then that's easy, right? I just become whatever my closest neighbor is. Okay, that's fine. It's not very sophisticated. What's kind of the far end that I could do? Well, I could look at my n nearest neighbors, but then what would happen? then each observation that I'm trying to predict is going to have the same outcome, right? Or the same predicted outcome, because I'm looking at what happened overall, mostly in my training set, right? So if I have a higher proportion of class 1s in my training set, then if I'm looking at my n nearest neighbors, then I just say, okay, well, I'm going to be in class 1 because that's what happened mostly in this data, right? That's not very useful. So we don't want to do that. And so we've got a little smaller values of k. So a k equals 1, where I just look at my closest neighbor, or 2, right? Then what we say is that they're more susceptible to noise in the training set, right? Because then it really looks at, you know, those 2 closest ones, or those 1 closest neighbors, right? While larger values of k, we might lose some of those features, those location dependent features, right, that we want to capture. So usually what we do, and I want to highlight this one here, we consider values from 1 to root n. So you don't want to go all the way to n, because then everyone's classified in the same group, and that's no fun, right? Although that is a method, right? Okay, well, what happened last year? That's what's going to happen this year, that type of thing, right? And so, so usually we would consider k equals 1 through root n. Now, we have the tools, we have the computers, we can pick and choose, right? And so what we can do is we can develop all these predictions for each one of these, k equals 1, k equals 2, k equals 3, k equals all the way up to root n. We can do that. We can look at different k's, and then we can pick the best model, right? That sounds like a good idea. So the best value of k can be determined by building models for a range of k values and then selecting the value of k star, right, which is just that specific k that yields the best results, which means the smallest classification error on the validation set. Okay. Oh yeah, haha. So if we use, oh yeah, so we apply it to the validation set, and then we have to apply it to the test set. Okay. So usually what we do is we look at a series, and maybe I'll make a note here, right? What we're saying here is we usually consider a range of values for k. Oops. Got a little dirt on here. Okay. So I hope, yeah. Maybe this isn't the table that I, so here, and I've got one where we consider a bunch of different k's, I'm sure of it. But first, here is some training data, okay? And what we're trying to predict is we're going to try to predict whether this person defaulted on a loan, okay? And maybe I won't put it up so close. All right, so for example, right, we want to predict loan defaults where ones means yes, they defaulted, and that's bad. It's bad in general, but definitely bad if you're the bank, right? So then you want to know can I predict who will default on their loan and who won't? Right, so 0 is no default given an observation's age and average account balance. Yeah. That seems like something that we would do in real life, and for sure banks are doing it. And so they've probably got more sophisticated models that they're using, right? They're not just looking at the average balance and the age, but those are probably the core players, right? And so it's not that far off. We can just extend it to more predictors if we wanted to. Okay. And so what we want to do here in our example specifically is, given an observation's age and average account balance. So now what we're saying is our task is to classify a new observation with an average balance of 900 and the age is 28. Okay, so we have this information. So we had a new applicant at the bank and we are told that their average balance is 900 and they are 28 years old. Okay, so that's the one that we're trying to predict. Okay. So what we can do is, of course, we can look and learn from the training data here, and we can map out the training data. Let's see here. Just gonna bring this in here because I want to mention that, but I also want to. Here's the one that I've been wanting to show, trying to bring up. And finally, we get to talk about it. It's just nice when you get to see, the data, right? One thing that I will say is usually what we do is if we have information like the average and the standard deviation of the average balance, what can you do? You can compute a Z-score, right? You can standardize this data. So a balance of 49 compared to an average of 1285, if the spread is 2029, right? Then we can standardize that value and we can get a Z-score. Okay, same thing for the age, which is just saying, okay, how far is an age of 26, for example, from the mean of 38.2, right? We standardize these values. Which is the Z-score, right? And Z is X minus mu over sigma, which in our case is going to be X minus X bar over S. Okay, because those are the means and the standard deviations that we have are from our sample, but that's okay. Okay. So let me do one, for example. Let's find this balance of 49. If I have a balance of 49 minus the average of 1285 divided by the spread of 2029, then I get negative 0.609. So let's see if I can find that guy. Negative 0.6. Hey. Oh, it's because I did the balance. I'm trying to put it on the age axis, but really, I'm like, I know it's here, but yeah, negative 0.6 So we had 49 minus 1285 over 2029, roughly negative 0.609. Let's say 1. And notice that this is, of course, a number scale, so centered on 0. As I move out further, right, it makes sense that this would be magnitudely, if that's a word. I'm not sure that's a word, but in magnitude, right, larger than negative 0.5. So whereas the age of 38 for observation 1, the age from 38.2, we expect it to not be very far, right? So if I take 38 minus 38.2, so that distance between the observation and the mean divided by 10.2, then I get negative 0.019. So let's just say negative 0.02. So here, (38 minus 38.2 divided by 10.2 is roughly negative 0.02. Okay. So now I have the X and the Y coordinates for observation number 1, and then you would be able to go through and find the X and the Y coordinates. Now, it is possible to put a third plane in here, right? And if you've taken any higher level calculus courses, right, you'd know that it looks like this kind of cube situation. But for simplicity's sake, let's just keep it to 2 variables, right? 2 predictors, X and Y. And but we're also going to have the outcome, which, because it's binary, right? If it's a dark spot, then it's a lone default, and if it's an open spot, then it's no default, right? And so here, this is class, oh, maybe I should do class 1, and these guys are class 0. Okay. So if it's a closed dot, then it's in class 1. If it's an open dot, it's in class 0. Okay. So what do? Well, the value that I'm trying to classify, I have to standardize it, of course. I had an average of 900, and then I had to standardize it, and that puts me a little bit below 0 because it's less than the mean in terms of the average balance. And then slightly lower, I think 26 years old, right? Pretty sure. 28. Close enough. Right, 28 compared to the average age, which was 38.2 with a spread of 10.2. So then we get this slightly less than 0 standardized age score. Okay, so this little guy here is the one that we're trying to learn about here. Okay. And what I'm going to do is I'm going to use this, this little feature that when I draw a circle, it'll make a perfect circle that I can adjust. Okay. So what I'm going to do is I'm going to go and find I'm going to let K be 1. Okay. If K is 1, then I find my first neighbor is in class 1. So what do I predict that I am? I predict that I am class 1. Okay. And so down here in the table, let me just blow this up a little bit here. What we've seen, right, is if K is 1, then the percentage of class 1 neighbors is 100% because I only looked at 1 and it happened to be in class 1. So I classify myself as being class 1. Okay. So now what I'm going to do is I'm going to go and find K equals 2. Okay. And so it's important, and I feel like it shifted here. It's important that it's centered on observation. That's hard to do, right? But so now I'm going to go until I hit my 2. Hey, what the? My 2 nearest neighbors. It's doing it, but it's not doing what I wanted it to do. Let's do this. There. So when k equals 2, I hit the 7th observation before I hit the 6th observation. It doesn't really matter, right? But now at k equals 2, okay, then I'm going to have a 50-50 split, right? Because one is in class 1 and one is not, right? One is in class 0, but I have a classification of 1. So I want to highlight that because that's one of those things that can be tricky, right? If I'm at 0.5, what do I do? Well, then let's just sit for safety's sake, say it's in class 1. Okay. Okay, so then what you can do, you can keep going, and I'll do one more here. 1, 2, 3. K equals 3. Now all of a sudden I have 2 in class 0 and only 1 in class 1. So now the probability or the percentage of class 1 neighbors is only 0.33. So then my classification has to be 0. Right? And remember, for this training data, we have the actual outcomes. We have the actual classifications. So then what you can do is you can compare these different Ks, right? And you can figure out, okay, which one performed better. You'd look at more than one observation, of course, in terms of the classifications, but that's the idea, right? So then you could move this little triangle, you could move it over a little bit, and in theory, you would use software. You wouldn't want to do this by hand by any means, but what you could do is you could span the entire space, right? Or some reasonable space, right? We can create classifications and k-nearest neighbor classifications at every point in this plane, right? So that's kind of cool. And then we would be able to predict any value, not just this one, right? Because if we think about it, then this whole plot, we could make it up by just putting tons and tons and tons of little triangles and then doing the predictions, k-nearest neighbors, and then summarizing that way. Okay, but that's how you do it for one, and then you would apply it to potentially the whole grid, right? Okay, so good. So once you have the predictions, right, or the classification predictions, then you would compare it to your actual outcomes and then determine the one with the least error. Okay, I think that's good. Now, if we talk about continuous outcomes, then the same thing happens, right? Now we're talking about continuous outcomes, which means that we're estimating, right? But for continuous outcomes, right now I have outcomes on some scale, and what I want to do is I'm going to take the average of the outcomes. I kind of already did that in the classification setting, because what did I do? Well, I looked and I basically became the average outcome of the k-nearest neighbors, right? And so, but here it makes more sense because it's not a 0-1 situation. So a new observation's outcome value is predicted to be the average of the outcome of its k-nearest neighbors in the training set. Okay. And so again, we're going to look through a range of possible values of k, and then pick the best value of k that's going to give us the least error in our predictions, okay, or in our estimations. Okay, so again, you can look at k equals 1. The average of one observation is just that observation, right? So then I just become what my nearest neighbor is. That might not be that useful. It could be, right? But so that's why we consider it. We usually consider k equals 1 because maybe that is a good way to do it, right? Depends on the situation. And then we don't want to go all the way up to n, because then everyone would be the average of all the n outcomes, which is an option, but it's not usually that good of an option. Okay? So the best value of k can be determined by building models over a typical range. So k equals 1, we consider k equals 1. And then now, instead of going to root n, we go to root n over 2. I don't know why, I just accept it as a fact. And then what you do is you take the k that gives you the smallest error. Okay. So in terms of a numerical outcome, let's see here. We can put it on some number line, right? For example, if I have the age, right? And so I can map the age, and then what I have is I have I want to say the account balances. So it's still referring to the account and the default data. Let me see here. Let me just confirm. We've got, yeah. Still considering the default data, or maybe I'll say the loan default data, otherwise default just means default. The loan default data, okay. But we now want to predict or want to estimate the account balance. The account balance is numerical, and we could have tried to estimate their age from their account balance. However, as a bank, maybe you don't feel comfortable asking someone's account balance, but you feel more comfortable asking their age, would be kind of the key idea here. Or if you're a lending, you know, maybe you're a loan shark. Oh, that's not good, right? Good for the loan shark though, right? So maybe you're a conscious loan shark, and you don't want to ask people how much they have in their account, but you do ask them how old they are, and they answer, and that's easy information to get. Whereas account information might be a little bit harder to get. So now what we're trying to do is, okay, if I know their age, can I estimate their account balance using the KNearest Neighbors approach? So we're still looking at that loan default data, but now we want to estimate the account balance given their age. Age equals 28 for our estimation. So again, right, if I have a numerical variable here, age, I've got this number line. The minimum was 26, I want to say, right? 26, maybe 27, 28, 29, right? And so we can focus down here and say, okay, this is at 26, this, oh, put it in the middle, 27, 28, 29, 30. Okay, so now on this number line, each point is going to have some account balance next to it. What's easy about the number line is it's obvious which values are the closest, right? So for one nearest neighbor, what do I predict? Well, that's my one nearest neighbor has 36 in their account, $36, I guess. Depending on where you are in school, that could be very realistic, right? And so kind of remembering those times, but so then if you've got a 28-year-old, then your KNearest neighbor, your one nearest neighbor is 29 years old and they have 36 in their account, and so that is what you estimate this 28-year-old has in their account. But if you go to two nearest neighbors, right, then you would go and take the average of 36 and 2100. This 30-year-olds live in large, 2100, right? So then the average would be 2100 plus 36 divided by 2, which puts me at 1068. So at two nearest neighbors, I have an estimated account balance of 1068. Wonder if I have the table in here. I can't remember. Oh, I do. Haha. Just bring in this just because, completeness sake. But this here is just what I blabbed about, right? So if you want clarification, then it's going to be in here for sure. But what I wanted to grab was this table, so I don't have to jot it down myself. Maybe I'll make this a bit smaller. Okay. Hey, that's not what I got for my two nearest neighbors. I got 1068. Yeah. Oh, because I'm at 28. So there's a tie between 30 and 26. That's the problem. So here, there's a distance of 2, and to 26 to 28, there's a distance of 2. So we have a tie, a distance tie. I was blabbing about it being a number line, and then we can see the distances, but then I forgot to use it. But from 26 to 28 is a distance of 2, but then from 28 to 30, which is the one that I was using for my average, because I don't know, I wasn't paying attention, is also a distance of 2. And so what we've got here in terms of the average, I guess I didn't talk about all of this. For k equals 2, we see that there's a tie. So what we would do, there are tie-breaking rules, of course, and depending on what software package you're using, or even what tool you're using. Maybe I'll just end the highlight there. In this example, we're just going to use all 3 as our estimate. Okay. And so that's what gives 936 and 936, because that's for our 2 nearest neighbors as well as our 3 nearest neighbors, because we had to use 3 for our 2 nearest neighbors. Okay. That's okay. So now we've got these average balance estimates, and what you'll see is that the average changes, right? So our estimate changes depending on how many neighbors we look at, right? So here it's got an upswing, and then it decreases to 750, and then it goes up to 19, 16, goes down to 13, 13, 11, 12, right? And so what we're going to find is that it's going to even out, and we want to find the one that has the best estimate for the account balance. Okay. We happen to know that it was actually 900, right? So then up here, we're doing a pretty good job of estimating, right? But we want to look at more than one observation, of course. And so that, and that's going to let us determine which one is the best model. Okay. And maybe I'll highlight where it talks about here, dink, like that. Okay. So that's our KNearest Neighbors, okay, which is a kind of a cute, fun section to talk about. And as soon as you've kind of figured out that, okay, I'm just looking out and seeing, okay, what's everyone else around me doing? And then that's KNearest Neighbors. Okay. I do want to talk a little bit. I know I'm I was scheduled to do this on Wednesday, but it might be nice to start talking about classification and regression trees. Although there's 2 pages here, what I want to do is I really just want to talk about them. It's not something that we are going to apply because it's a huge field of study, and so it's part of machine learning, and which is all cool stuff. But here I just want to introduce the concepts to you, and then you know, throw a couple of other things at you in the ensemble methods, where we you know, consider a series of trees instead. And then there are some other things that we can talk about, but really I might just let you read through that on your own. And of course, you can read the section in the textbook as well. Okay, but what I want to do is I just want to talk about classification and regression trees. And we can use classification, or CART, classification and regression trees. Let me put that down here. We can use them for categorical outcomes, and we can use them for numerical outcomes. So if you hear CART, it's classification and regression trees. Okay? So what they do is they identify some data, right? So you have some data with tons of information, and you want to divide these into groups. And we're going to start, and we're going to look at the classification, okay? And we're going to focus on 0, 1 outcomes, but then we're going to look at regression and numerical outcomes as well. But remember, here in this section, we present a general description of what the CART logic is, right? And then we will leave the application to a different course. I don't know which one. I'm sure you do it, but if you don't, well, you should. Anyway, so CART, we're just introducing what is it, so that when you actually have to do it, then you have some idea of what the goal is. Now imagine maybe you are the bank, right? And you've got these who defaults on their loan information, and then you've got information on who doesn't default on their loan. So what you would want to do, and what a regression, a cart, so a tree does, is it splits the data and it keeps splitting it until we've removed all the impurity, we call it, right? So when we have a group with a couple of ones and a couple of zeros, right? So maybe there are 5 ones in the group and 2 zeros, there's still some impurity there until we've split it to have our zeros are classified in one section and our ones are classified in another section. Then we have zero impurity, right? Because everyone who's been lumped together in that group has the same classification. Okay. And so what we do is we look at the most obvious divider, right? And so maybe age is the most obvious divider. For example, if you are younger than 35 years old, you are more likely to default on your loan, for example, right? I don't know that, I'm making that up, but just for something tangible. So then we've got this tree where, okay, if you're over 36 years old, then you are being predicted to default on your loan, right? But maybe there's another one, right? If you have less than $2,000 in your bank account, then you're going to be further classified as a zero. Then you're for sure a zero, right? Maybe something like that. If you have more than 2,000, then you might be classified as a 1. And then maybe there's another kind of qualifier that we could look at to further split these bank clients up. Okay. And so what you're trying to do is you're trying to find cutoffs in your data, considering different variables that allow you to divvy up your groups so that you can say, okay, all applicants at the bank who are less than, let's say 25 years old, because you can introduce that age variable again, right? Less than 25 years old and have less than $1,000 in their bank account, they're all going to default on their loan. I don't know, I'm making it up. But so kind of a cool idea, okay? And it's definitely easier to think about when we have categorical outcomes, I think. Yeah. So here in this example, we want to, we're trying to classify an email as a spam email, depending on the number of $ and exclamation marks that are in the document. There are also things, so those aren't the only 2 variables that you could look at, but they help, right? So you can consider the number of spaces, you can consider the number of digits compared to the number of letters, right? And so there are lots of things that your email account uses to classify an email as spam, right? Does it go in the junk folder or not, right? Is it allowed to go and be free in your inbox? Okay, so here, this example is classifying an email as spam. So that's class 1, or junk mail, given information on the proportion of $ and proportion of exclamation points. Okay. So what we are looking at here is, maybe I'll try to make it even bigger so that we can draw on it, hopefully. Okay. So what we get an email and we gather information on the proportion of dollar signs and the proportion of exclamation marks. Okay, so we have some proportion, and what we do in our first step is we look at the proportion of dollar signs. We find that that is going to help us split our groups completely and do a pretty good job of just separating our groups. Okay, and so here on this branch we have less than 0.0555, and here we have greater than 0.0555. Okay, so that's going to be our cutoff, and that depends on our training data, right? But that's what we're going to take and apply to our validation set later to see how well it performs. Okay, and so here we've divvied up our data, and we find that 28 out of 46, I think it is 28 plus 18. So N is 46. Okay. So 28 out of those 46 had less than 0.0555 dollar signs, so they were kind of grouped as one. Or they had 18 of them had more than 0.055 dollar signs, so they were sent down separate branches. Okay. Then what we did is if they have less than 0.0555 dollar signs, then we determined that, okay, to further split these guys up, then if they had less than 0.0735 exclamation points, they are all going to be in class 0, not spam. Not spam. Okay, and there were 21 of those that satisfied that criteria. So that's a pretty good indicator that, okay, this is a good divisor, right? Okay, so I have less than 0.055 dollar signs, and then I also had less than 0.0735 exclamation marks. Then all of those were not spam. That's good, right? So then we're done with that group. 21 of those are out of the picture. They've been classified as not spam, and they are not spam. Okay, so then what if you have more, and this less than, greater than applies to the left-hand side and the right-hand side of each branch, right? So here's is less than, oops, here it's, I think it's less than or equal to 0.0735, and here it's greater than 0.0735. Pretty sure it's equal. I'd have to check, but you can take my word for it, I guess. Okay, so then if they had more than 0.0735 exclamation points, right, something's getting fishy here. So then 7 of them satisfied that criteria. So then what we did was break it down even further, right? Okay, so what if you have less than 0.2665 exclamation marks? 4 of those were found to satisfy that criteria. And then we said, okay, based on the exclamation points again, then if it's less than 0.0985, you're classified as a 1, and only one observation was that, right? And if it's more than 0.095, but less than 0.2665, then 3 of those were class 0, right? So it splits up this, your classifications, and you introduce these nodes, right? So all of these are nodes, and it divvies up the entire data set, right? Until you, everyone has been correctly classified, right? Okay, nice. Okay. Okay. Struggling because I know I'm kind of out of time here soon, but so I don't want to. But maybe what I'll do is I'll try to finish the classification trees, and then you can read the regression trees for next day. Okay, so after we have this final tree, so this tree that we were just looking at, now I can take a new observation, right? And I can take it through this tree, right? And it kind of becomes like that game, Guess Who, right? Do you remember that game where you were playing and you had to, oh, are you a man or a woman, right? That would be your first question probably when you're playing that game. And so that would be your first note. Do you have less than $0.0555 signs or more than $0.0555 signs? Just doesn't make that nice of a game anymore, but it's the same idea, right? And then so that's your biggest branch. And then you would classify based on how you went down each of these branches. Okay, nice. And so notice that we're incorporating the dollar variable and the exclamation variable, and then we can go back to the dollar variable if we find that we need to. If we find that that's the most telling piece of information that we have, then we can go back to that dollar variable, right? In this branch, it all kind of was hinging on the exclamation, but we could just as well go back to the dollar variable and use that as kind of a cutoff. Okay. Okay, so, well, I'm obviously not going to finish here, but that's okay. Got Wednesday. So what I want you to do is just read through the remainder of these summary notes so that you have, you know, some, or the textbook, I guess, but at the very minimum this, and then so then when we can just talk about it, we can just talk about it conceptually. Okay, so, and then you've got the caret at the end, right? Once you have read and hopefully understood the notes up to this point, then that's it. So you got this. All right, so that's what we're going to finish next day. And then it'll be on quiz number 4. And then that's it. So if you have any questions, let me know. Otherwise, we'll pick up there on Wednesday. All right, stop this.